So this lesson is about sketching tangent and cotangent. Like I said last week, we're going to take a graphical viewpoints of every single trig function two at a time. Last Friday we did sines and cosines. Today we'll take a look at tangent and cotangent. Well, first things first, let's just see what the heck this guy looks like. So again, break out a graphing calculator, break out Desmos, and we can actually plot tangents. And I already went ahead and did it for us. So you can see here how tangent looks pretty. Oops, that's not what I want to do. Let's zoom back in. You can see tangent is very distinct from sine and cosine. There are a lot of similarities, yet most distinctly differences. And the reason why tangent and in extension cotangent looks so dramatically different versus sines and cosines is by how it's defined. Recall the definition or the graphical definition of tangent. For any value or for any angle theta, the tangent of theta is the sine function divided by the cosine function. Remember how when we saw when we put a circle on a Cartesian plane, we saw that tangent was y over x, but y was sine and x was cosine. So tangent, by definition, is the ratio of sine and cosine. It is a rational function. And we saw rational functions, I think, in Unit 4, maybe Unit 5, that one distinct characteristics of rational functions are vertical asymptotes. So if we take a look at the graph again, we can see that this function here indeed has vertical asymptotes. It looks like we have vertical asymptotes at negative pi halves, positive pi halves, 3 pi halves, 5 pi halves, all of the odd halves of pi. Now, why is that the case? Well, tangent, his denominator is cosine. So if I take a look at the cosine graph superimposed on the tangent graph, we can see that the tangent graph has vertical asymptotes whenever cosine equals 0. And that should make sense, because vertical asymptotes exist wherever you're trying to divide by 0. So because cosine is the denominator of the tangent function, the tangent sort of does the opposite of whatever cosine does. Whenever cosine is getting bigger, tangent gets smaller to 0. Whenever cosine is getting towards 0, the tangent function gets bigger, 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 all the way to infinity, positive or negative, depending on the symbol of cosine. Right. So just so I don't have to constantly flip back and forth, I sort of want to, just for the sake of completeness of notes, I'll just go ahead and take a snippet of this picture here. I suppose you could include it in your own notebooks if you want, but again, you can easily recreate this by using a graphing calculator or popping on Desmos. I'm just going to go ahead for the video, just so I don't have to constantly flip back and forth, include it. So let's paste this here. There we go. So here is basically the tangent function. Now, I want to note some similarities and differences. Let's start with the differences. Differences in the tangent function from the sine and cosine. Notice how when we analyze sine and cosine, we want to take a look at one full cycle, one full period starting at 0. But I think everyone can agree that the full shape or the full cycle of tangent is a swish shape here. And we do not get a complete shape starting at 0. As a matter of fact, starting at 0, we only get half of the shape. So that's sort of the difference between tangent compared to sines and cosines. I can't start at 0 when if I want to take a complete picture of the tangent. I actually have to start at negative pi halves. So the full picture of tangent starts at negative pi halves instead of 0. Secondly, this is the full picture here of tangents. Notice it's between the vertical asymptotes of negative pi halves, positive pi halves. So by definition, the horizontal length is the period. So what is the horizontal length between negative pi halves and positive pi halves? That is 1 full pi. So it has a period of 1 pi. Whereas on Friday, we saw that sines and cosines have a period of 2 pi. And last but not least, there's no max, min, or amplitude. We saw that on Friday, amplitude, that sine and cosine are bounded or trapped between positive 1 and negative 1. But clearly, this tangent function will go up forever, will go down forever. Its range is all real numbers. But there are some similarities with sines and cosines that can help us sketch. Right? Phase shifts, and really all the transformations, affect the graph. No function is exempt from function transformations. Right? And while tangent doesn't have an equilibrium line or a sinusoidal axis or a principal axis, because it really doesn't balance, it doesn't really oscillate or bounce back and forth between a particular line, it still has sort of a zero or a midline. That we can exploit when it comes to sketching. So what are the parts of a tangent graph, right? So on Friday, we talked about the general equation of sine and cosine. We have the general equation for tangent. And it's going to look 100% the same as the sines and cosines, except, different trig function. Y equals A tan of B times X minus C plus D. The parts will be slightly different, but they're basically the same. D is the midline. Again, I'm putting the midline in quotes because it really isn't. There's no such thing. Y equals D, but I'm going to use it to help me graph. C is still our phase shift, which is a fancy trig way of saying left or right. And B affects the period. Now for sines and cosines, it was 2 pi. The formula is 2 pi over b. But since this is a tangent function, it's only going to be 1 pi over b. That's something you need to remember. Now what does A do? Well, since we don't have an amplitude, it's sort of hard to pinpoint what A does. Well, if we sort of take a look at the parent function for tangent, let me go ahead and pull up Desmos again. Let's see if I can zoom in to quarters. Okay, here we go. And let me take a snippet here. What the A affects are what I like to call quarter points. Oops. So the 5 special points of the tangent function is negative pi halves, negative pi quarters, 0, pi quarters, and pi halves, because these are the vertical asymptotes. So this is one full cycle here. You notice how at these quarter points, that pi quarters, this is a very easy to read point. This is a very easy to read point. So this right here is what A will affect. It will affect this scaling here. So while tangent doesn't have an amplitude, in order to make our graphs somewhat presentable, somewhat accurate, these quarter points or these middle points is what we're looking for. Last but not least, we need to know the shape, right? So for a positive tangent, we can just see that one cycle will look something like this. So a negative tangent should be the exact opposite. The reason why I'm harping on the shape is because the pattern will be the same no matter if you have a positive or negative. So when it comes down to sketching, knowing the shape is critical. So we can see at these 5 special points, just like sines and cosines, the pattern goes, you start with the vertical asymptotes, then you go into your a value, then you go to the point that's on your midline, go back to your a value, and then you go to the vertical asymptotes. Whether or not these go up or down from the midline will depend on the shape. So you can see in a positive tangent, to the left, the a goes down, and to the right, the a goes up. So the way you sketch will be basically the same process as sketching sines and cosines with one key difference. For sine and cosine, your interval was 0 to whatever your period is. For tangent and in extension cotangent, actually cotangent's different. For tangent, your interval will be negative whatever your period is over 2, comma, whatever your period is over 2. Because the full picture of tangents starts in the negative region, you have to split your period in half first. Other than that, everything will be the same. You read your function transformations, you find your intervals, you find your 5 critical values, you do the right pattern, you plot, you go home, be happy. So for example, suppose I ask you to sketch y equals 2 tangent of 1/2 x minus pi fourths minus 1. So first thing I do is I just read all the information I can. So my midline is at y equals -1. I have a right by pi fourths. My period will be pi over 1/2, which happens to be 2 pi. And my a is 2. So it's not an amplitude, but it's still important. Now this is where things get different. I have to take half of the period, so half of 2 pi is 1 pi, and make it negative. So that's what I start with. Then I go with my phase shift, which is right by pi fourths, and then I get -3 pi fourths, comma 5 pi fourths. So that right there, this guy here is the only thing that's really different. I guess this is different too, this period formula. Those two guys are the only difference between today and last Friday. The rest is still basically the same, right? Make your XY table, find your 5 critical X values. And to find your 5 critical X values, it's nothing but taking averages. So you start with -3 pi fourths, 5 pi fourths. In the middle here is the average of those two numbers. So add them up, divide by 2, you can get a pi fourths. So this guy here, you can add these two numbers, divide by 2. That's going to give you a negative pi fourths. And then last but not least, a positive 3 pi fourths. Now I have to know the pattern because I can just mentally memorize that it's a positive tangent. You're going to have vertical asymptotes, a mid, a vertical asymptotes. My mid is at -1. And since my a is 2, I know that these guys will go up and down by 2. Again, knowing the shape of positive tangent, it's going to go down to the left and up to the right. So down 2 to the left would be -3. Up 2 to the right would be a positive 1. Then all I got to do is draw it out. So I'm going to make a pretty long, I'm running out of space here, x-axis, but whatever suits your purposes. And again, I'm not going to be too picky, but just try to make it somewhat reasonable. So pi fourths, 3 pi fourths. I have a positive 1, a -1, -3. I know my mid is at -1. I know my vertical asymptotes are at the endpoints. And I know it goes down to the left, up to the right. And there is my not so pretty graph, because I should have made this guy longer. But, you know, as long as you have all the points labeled, I am A-okay, right? Basically, the chart is the most important thing. That'll let me know whether or not you understand it. The graph is just to make sure that you have the right shape in mind. But that's it. That's all you got to do. So it's basically a rehash of Friday's lesson, except you got a couple of changes and a new shape. Just for good measure, let's just do a negative tangent example. So say I ask you to sketch negative tangent of 2x plus pi plus 2. Notice this is not in the right format. I don't want this number in front of x. I want to factor him out. So we should have seen this on Friday's practice. Before I do anything, I need to factor out that 2. And remember, factoring is the same thing as dividing. So if I want to factor out a 2 from pi, that's the same thing as dividing pi by 2. So now that it's in the right format, I can go ahead and read the pieces. So my midline is at y equals 2. I have a left by pi halves. My period is going to be pi divided by that number. And my a is 1. And I got to flip. So since my period is pi halves, my interval will be negative half of him. So half of a half is a fourth, comma, the positive. But I have a phase shift of left by pi halves, which means if I do some quick subtraction, that's going to be negative 3 pi fourths, comma, negative pi fourths. So then I can make my XY table. 1, 2, 3, 4, 5. I know my intervals between negative 3 pi fourths and negative pi fourths. And then just take a whole bunch of averages. So right smack dab in the middle, add them up, divide by 2, negative pi halves. To the left here, add them up, divide by 2, negative 5 pi eighths. Here, add them up, divide by 2, negative 3 pi eighths. The pattern, flip or not, is still vertical asymptote A, midline, a vertical asymptote, but the only thing that's different, since I have a flip, since I have a negative tangent, I know that's going to be, well, not that extreme, that's going to be my shape here. So my midline is at 2, but now I'm going up A to the left, so since A was 1, I'm going to go up 1 to the left, which is 3, and down 1 to the right, which is 1. So then I'm going to sketch. I'm going to draw a bit more, since all my special x values are negative, I'm going to draw, well, I guess this guy goes in both directions, so that doesn't really help me. A pretty big negative. Let's see here. Let's make this, I don't know, negative pi fourths, negative 3 pi eighths, negative pi halves. No, that's not really to scale. Oh well. Negative 5 pi eighths, negative 3 pi fourths. Let's see here. My special y values are 1, 2, and 3. Midline at 2. Vertical asymptotes at the ends here. And since it's a negative tangent, I know to the left he goes up, to the right he goes down, in the middle is midline. And again, it's going to be a very ugly picture because ours is not to scale, but as long as you jot everything down, label everything down, that is acceptable. So that's tangent. How does things change with cotangent? Well, let's just go to Desmos. This one I actually didn't prepare, so I'm going to actually have to type it in. Oops. Here, so let's deactivate that. Let's add one more. Y equals cotangent of x. And it looks like it's basically the same shape, which is good for us. That means we don't have to memorize anything new. But there's one interesting thing here. Let me superimpose things. Just like what sine and cosine are basically the same shape except shifted over. Tangent and cotangent are very similar shapes except two things. Number one, they seem to be shifted over. You see how at the origin, tangent goes through the origin, but cotangent does not. And the second thing is their patterns are completely flip-flopped. So let's go ahead and I'll just, for the record of our notes, I'll try to take a snippet here. Hopefully that's not too big. So here is sort of the basic parent function of cotangent. And there are some things that we can see that are same and some things that are not. So we can see that it does have vertical asymptotes. But in this case here, the vertical asymptotes are at 0 and pi because cotangent is cosine over sine, so it has vertical asymptotes whenever sine is 0. And we saw that sine does start at 0 and go through pi. So the similarities are it does have a vertical asymptote. What is this period? It's still 1 pi. And it has a similar shape. It's not 100% identical. The important thing is it does have an opposite pattern of tangent, though. In this case, what we see here is a positive cotangent. We see a positive cotangent looks something like this, whereas a negative cotangent would look like a positive tangent. So you got to be very careful with tangents and cotangents. They share opposite shapes. And another important thing is that cotangent starts at 0. So the interval that we always start with is 0, comma, whatever the period is. So sines, cosines, cotangents, basically the rule of thumb is every single function, the interval at least, will start at 0, comma, whatever your period is, except for tangent. Tangent, you got to split in half, positive and negative. But other than that, guys, I promise you, the way to sketch these guys is 100% the same. So let's go ahead and do a couple of examples here. Suppose I ask you to sketch y equals 3, cotangent of pi halves, comma, x minus 1 minus 3. Let's read all of the pieces, and it will be the same reading as tangents. So my midline is y equals negative 3. I have a right 1. My period is pi, just like tangent, pi over pi halves, which ends up being 2. And then my a value is 3. Because this is a cotangent, I will start at 0, comma, whatever the period is, but I had a right 1, so my new viewing window is 1, comma, 3. Finding my critical x values should be easy because these are regular whole numbers, 1 and 3. So 2, 3 halves, or 1 point, let's just use 1.5 since they're regular whole numbers, and 2.5. And then the pattern is going to be the same, vertical asymptote, A, mid, A, vertical asymptote. So tangents and cotangents are super duper easy. They all have the same pattern, positive, negative, cotangent, tangent. The important thing is shape. A positive cotangent would have a negative tangent shape. In other words, it'll look something like this. So if my midline is at negative 3, I go up by A to the left, which is 0, and down by A to the right, which is negative 6. And then that's it. Just draw your shapes and you're done. Be happy. So we have 1, 2, 3. Let's see here. I had a lot of negatives, so I'm going to scroll down. 1, 2, 3, 4, 5, 6. So 0 is important, negative 3 is important, negative 6 is important. min line at -3. I have a vertical asymptote at 1 here. 1.5, 2, 2.5, 3. Vertical asymptote at 1, at 3. Let's see here. My mid is at 2. Up and to the left, down and to the right. Very narrow graph. But there we go. I mean, again, it's not pretty, but as long as you label everything, as long as I have that table there, you should be good to go. So that's it. That's sketching tangent and cotangent. And of course, if I were to make this function negative, you would just obviously have to remember the shape of a negative cotangent. But that's it. To sketch these trig functions, they're going to be very similar in terms of processes. You just have to remember those subtle differences. Good luck.